Hello, my name is Hans Hartmann, and today I like to talk about DDR3 routing on inner versus on outer layers. I will use as an example board the BeagleBone black board. I will open the PCB layout data in a signal integrity analysis tool. We will review a little bit how the routing was done, and we talk about the PCB stack-up, and then in particular I like to talk about the DDR3 address lines, and then I will do some conclusion. Here we see the PCB layout opened in a signal integrity analysis tool. To review a little bit how the routing was done, we see it's a 6-layer board. We see in this area the Texas Instruments Citara processor. We see here in this area the DDR3 low power memory, and in my project I used Micron devices, and I also downloaded from the websites of the component makers, I downloaded the IBIS simulation models of the two parts. So let's look at how the routing is done. So we see in this area there is some amount of routing on the top layer. On layer 2 we have a ground plane. Then we have some amount of DDR3 signal routing on the layer 3. On layer 4 we don't have any of the DDR3 signals. And then we have on layer 5 a power plane layer with some power planes, and on layer 6, on the bottom layer, we also have some amount of traces routed here. For example, in this area we have also address lines. Next, in order to do something meaningful with the signal integrity tool, we need to review the PCB stack-up so that the field solver, which is used in such softwares, can make the proper calculations. For this, we have a stack-up editor in which we actually model how the real board is manufactured. So we model all the layers that we have. We provide the thicknesses that we ask the bare board fabricator to manufacture. We provide the parameters about the dielectric materials. So those are material parameters which we would get from the bare board fabricator, like the epsilon r of the dielectrics and the loss tangent of the dielectrics. And what we can do is to make some cross-verification of the impedances. So I looked at the PCB layout data and I saw that the DDR3 address lines are routed on top, on bottom layer in trace widths of 4.8 mil, and are routed in the inner layer 3 using a trace width of 5.3 mils. So following this stack up and the material parameters we gave, it means that our address lines would have impedances of about 43 ohms on the outer layers and about 49 ohms on the inner layers. Next, I like to look at the address lines. So let's see where they are. First, let's filter them. And on this board I use a 4 gigabit memory, which has in the simulation model address lines A0 to A14. So I select them. I saw one thing, that the trace lengths are given in in inch. So, but I like to show them in metric measures. So we can more easily see that all the address lines are tuned or matched to a length of about 2.4 centimeter plus minus 0.1 millimeter, which means the address lines are matched plus minus 100 micrometers, or about plus minus 4 mils. So this is a good matching. Now, what would we assume if we have such a matching? So the length is matched plus minus 0.1 millimeter. So there is a rule of thumb on typical printed circuit board materials, which means our signals travel about 0.15 millimeters per picosecond, which means if we see such an address bus nicely matched, we would expect about less than 1 picosecond of skew. Now let's validate if this is really as nice as we expect at first glance. In order to do further analysis, I prefer to bring all those traces into some kind of schematic mode where I can better see certain things. So I export this into what we call a freeform schematic. I give the file a name and make the export. Give it a little bit time. Okay, finished. Now what we nicely see here is all the 15 address lines. And we nicely see, for example, address line A4, it starts at the Citara processor. It takes a small routing, or in this case a little bit longer routing of 1 centimeter, going into a through-hole via from layer top to inner layer 3, and then some amount of routing on the inner layer 3, and then going again from layer 3 to the top layer into the memory device. So we can see this for all the address lines. We can see for each routed trace its representation as a transmission line model, and we can see the impedances which are derived from the stack up and the trace geometries. On such a thing like a via symbol, I can double click and even see the via characteristics, so I can see under this given stack up with this via geometries, I can see that a routing from the top layer to the inner layer 3 is equivalent to a delay of 2 picoseconds, while, for example, in this case here, we have routing from top to bottom, And in this case, we can see that a trace going through the via from top to bottom will have a delay of 18 picoseconds. So again, in previous statements we said our expectation is, because of the very nicely matched address bus, we have only a picosecond of skew. Now let's do a simulation. I downloaded, as I said, IBIS simulation models for the Citara processor as well as for the Micron DDR3 low power memories. I have several options to do a simulation, but for this purpose I make a very simple one with an oscilloscope where I set up maybe 400 megahertz that I like to simulate. I make everything nicely into the view. So I see the waveforms on both my memory controller, which is the ARM processor, and the receiver chips, which are the DDR3 memories. In this moment, I'm only interested to watch the curves on my DDR3 memories. And maybe zoom somewhere here, where we see all the address lines and the different arrival times at the memory chips. Now I can do a lot of things in this scope, but in this moment I'm only interested to get my fastest arrival time and about my latest arrival time. We don't need to be very precise for this exercise, and we see here an amount of 135 picoseconds of skew. So why is this? We nicely matched all the address lines about plus minus 100 micrometers, but we are getting such a huge skew. Now, one answer to this was already given, because we have seen that the matching which many PCB layout tools are doing is only calculating the trace lengths, but not considering the different delays through the vias when I have a top to inner layer via construction versus a top to bottom via layer construction. In this stack up we saw there is a difference of, what was it, 2 versus 18, so 16 picoseconds difference. So the address line A11 versus the address line A4, because of these two vias zoom up to 4 picoseconds delay, while for example these two vias zoom up to what did I say, 18, so 36 picoseconds delay. Now, but the different lengths in vias is not the only contributor to different delay. We have more contributors, and the title of my web presentation was inner layer versus outer layer. So I like to show what is the characteristic of a certain trace length in this stack up on a certain routing layer. So we like to compare. I copy and paste. So I have a trace segment and I say, trace segment, you are on bottom layer, and let's assume for comparison a 2 centimeter trace on the bottom layer with this width. So we have an impedance about our 53 ohms and we have a delay of 115 picoseconds. Okay. Next, I take a trace from an inner layer, copy, paste. I give this trace in the inner layer 3 also a length of 2 centimeters. And in order to approximately get as well the 50 ohms impedance, we had used in the layout a different trace width. But the important difference we are seeing is that the trace in the inner layer with 2 centimeters length will have a delay of 141 picoseconds, whereas the trace on the outer layer of the same length will have a different delay. And that is why we see, even so our address bus is nicely matched in terms of trace length, we see a difference in timing. Now, what is my conclusion then? So my conclusion is, when routing high-speed lines, consider if length matching is sufficient or if time of flight matching is advised. If you don't have a PCB layout tool that can support time of flight matching, examples for PCB layout tools which can do time of flight matching would be PATS Professional, for example, or Expedition Enterprise. But if your used PCB tool does not allow for this, then be aware that you put the constraints in such a way that you compare, so to say, apples to apples. That means compare lengths on layers which have similar signal propagation times. Now, a further conclusion, in my view, is that we have seen the BeagleBone Black project and the layout data I found in the web. And this is a proven piece of hardware. So no doubt the BeagleBoard is working. Nevertheless, in order to even make working hardware even more robust and maybe performing better in terms of EMI, we can use such type of analysis tools as shown. So, thank you for watching my video. If you like to send me comments, you see here my contact details, and I'm a Mentor Graphics reseller and technical support organization. And if you are interested in learning more about PATS hyperlinks, please contact us and ask for a free evaluation. Thank you for watching.